Hello, students. So now we want to take a look at 10.3. And in 10.2, we did a big introduction to polar coordinates. And in 10.3, we're going to continue with that, but we're going to do calculus in polar coordinates. This will work for me. So there's two primary things we want to do in this calculus in polar section. And the first one is we want to look at derivatives, basically. Not derivatives of polar functions, but just the derivative like we first introduced it, which is the slope of a tangent line. So since we can have a graph in polar, we can want to have the slope of a tangent to that graph in polar. And that's what I'm going to focus on in this video. And then that's only the first couple pages of the section. So then the rest of the section has to do with getting the area under a polar curve, and that'll involve integration, and we'll look at that in the next video. So let's get right to the heart of it. So let's say you had some polar graph, and I'll just sketch in something silly here. So let's say we had some graph with a loop in it or something that was swept out in polar coordinates. Well, then you can have a point on that graph, and then you can say, well, what is the tangent line to that graph? Just like back when we first started to talk about tangent lines to motivate calculus. So since you already know the point on that line, well then, in order to know that line, you would need to know the slope. And the slope is clearly defined. It's dy dx. And I say that because the slope goes all the way back to algebra as the rise over the run, and the rise and the run are measurements of horizontal and vertical directional changes. So even though in polar you're looking at angles and radial distances, rise over run of a line is still rise over run. So that means we want to find dy dx. We want to find dy dx, but we're working in polar. So what are we starting with? We have some function in polar, like maybe r is, let's see here, there we go. R is equal to some function in theta, 2 theta or sine theta or whatever the heck it is. So you plug theta into an expression on the right and you figure out the R value. But what we want is dy dx, and y and x are Cartesian variables. So what we want to do is remind ourselves, first of all, that there's a relationship between these, namely that x is equal to r times cosine theta, and y is equal to r times sine theta. So how can we get dy dx? Well, let me put it this way. Since we have a relationship between x and theta and r in the first and second equations here, we could, for example, differentiate x and y with respect to theta. We could get dx d theta. We could get dy d theta. So the way we're going to get dy dx is recognize that this can be achieved if you have dy d theta over dx d theta. So the way we do this is we need to eliminate the r variable. And so r is f of theta. So now take these two equations and let's modify them with this substitution with r is equal to f of theta, and that you get x, instead of writing r, is f of theta times cosine theta, and y is f of theta instead of r times sine theta. And then what you'll note is that we have parametric equations, like we talked about in 10.1, because we have two equations, one for x, one for y, both written in terms of the variable theta. Instead of t, we're using a theta. And in 10.1, we got dy dx the same way, by getting dy dt over dx dt. So we're going to do the same thing for polar coordinates when written all in terms of theta, by getting dy d theta over dx d theta. Now, in order to do that, however, we have to see that x and y are both written in terms of theta as a product of functions. So when we take the derivative, we have to use the product rule, which we can do. So if I take the derivative of the x with respect to theta, then using the product rule, I would get the derivative of the left, which would be f prime of theta times the right, cosine theta, plus the derivative of the right. The derivative of cosine is minus sine theta, times the left, which is f of theta. So similarly, maybe I'll erase some of my little tangent line here. If I want to get dy d theta, then I'd get the derivative of the left times the right, which now is the sine function, plus the derivative of the right, which is now cosine theta, times the left. So what I have now is functions in theta which give you dx d theta and dy d theta. And if I make a ratio of dy d theta over dx d theta, I get dy d theta. So this is going to give us a formula. So dy dx is dy d theta divided by dx d theta. And so dy d theta was f prime of theta times sine theta plus, and I'm going to write the function on the left, I think that's the way the book does it, f of theta times cosine theta. So that's dy d theta. And then I'm going to divide that by dx d theta, so that's f prime of theta, but now times cosine instead of sine. And I have plus a minus sign, so I'm going to write minus and write the function on the left, f of theta times sine theta. And this is our function in theta, which gives us dy dx, gives us the slope of the tangent to the point when you specify the angle theta for the polar function. So let me just give a reference. So they go through this process for you as well. This you can see on page 733. All right, so this basically gives us a big fat formula for dy dx. And this, again, if you look in the formula, it all is in terms of theta. So that means that if you give me a function and a point of theta for tangency, so I know where the tangent point is, I can plug that in and figure out what the slope of the tangent is. So they do some examples, of course, for you. I figure I will do one. Again, this is only 2 pages of this section, but let's do an example from the exercise set to try to just show this formula in action. So that's on page 738. So on page 738, we'll do one of the exercises. This is the end of the section. Lucky number 7, maybe? Looks good. So the instructions are to find the slope of the line tangent to the following curve at the given point. And the curve in number 7 is r is equal to 8 sine theta. And there's a point given. The point is 4, 5 pi over 6. Is that right? Yes, that is right. Okay, so we're still getting used to the fact that when you're given points in polar, the input variable is on the right instead of on the left. You're normally thinking x, y, and x is the starting value and y is the answer. But when you're given the r theta, theta is the starting value and r is the answer because you're given r as a function of theta, but we just have to get used to that. And we have our function here. Okay, so in order to use the formula right above it, I need to be able to plug the theta value, 5 pi over 6, into the function itself, into cosine, into sine and into the derivative of the function. So if I start with the function, f of 5 pi over 6 is, what's my function? 8 sine theta, so it's 8 times sine of 5 pi over 6. So let's see, 5 pi over 6 is 1/6 up above pi, so it's in the second quadrant, and the y value is sines is 1/2. So this would be 8 times 1/2, or 4. So I just figured out this part of the formula up here. This part right here. Sorry, I just got that wrong. Good thing I'm double checking this part. So I need to evaluate the function at theta in both the numerator and the denominator, and theta is 5 pi over 6, so I plug that into the function and I got 4. All right, so now I'm going to need to also do the derivative for the top and the bottom of the function. So I'm going to plug into the derivative next. So I want to find the derivative evaluated at 5 pi over 6. So the derivative of 8 times sine is 8 times cosine, and I'm plugging in 5 pi over 6. Okay, I'm in the second quadrant, 1 pi over 6 up from pi, and I want the x value, so in the second quadrant that would be negative. And instead of 1/2, I would have the square root of 3 over 2, so that should be negative square root of 3 over 2. So what is that? That's cosine of 5 pi over 6. And if I multiply these together, I think I would get negative 4 square root of 3. So I now know the value of the function evaluated at theta. I now know the value of the derivative of the function evaluated at theta. And I need to know the value of sine and cosine evaluated at theta. But luckily, since the function had a sine in it, I've already evaluated sine and cosine at theta to get the answers in here. So I can just use all of this to plug into the derivative formula. So let's just go ahead and go forward with that. So that means that dy dx is going to be equal to the derivative at theta, which turned out to be minus 4 times the square root of 3, times sine at theta, which turned out to be 1/2, plus the function at theta, which turned out to be 4, times cosine of theta, which turned out to be minus square root of 3 over 2. So that's the numerator of our formula for the derivative, or for dy dx specifically. So then on the bottom, again, I need the derivative of the function, same as above, but then instead of the sine, I need the cosine, minus root 3 over 2. And I then need the value of the function, same as above, but then instead of the cosine in the top, I need the sine, which was 1/2. So I've at least determined the value of each of the pieces in the formula. Now we just need to simplify. So multiplying the 4s, each of them is divided by 2. Let's see. So I'm going to get negative 2 times the square root of 3, and another negative 2 times the square root of 3. And then over here, I'm going to get negative times negative is positive on the bottom left. 4 divided by 2 is 2. Square root of 3 times square root of 3 is 3. So I think I get positive 6. Plus 4 times 1/2 is 2. Okay. Except I miscopied a minus. I'm seeing, I was going to say, why is there a plus down there? There's supposed to be a minus. So here's my mistake. I'll show you, and then I'll fix it. This, I wrote a plus, but up here in the formula, it's a minus. So maybe some of you watching this caught that before I did, but at least I did catch it. So I'm going to fix that here and make that a minus. Yeah, when I got over here, I was like, I thought there's a minus in the bottom with this formula. And there is. Okay, so that means that I get a 4 in the bottom. 6 minus 2 is 4. And the top, if I combine like terms, I get negative 4 the square root of 3. And the 4's are going to cancel. So it should just end up with negative square root of 3. I think that's right. Okay, so what happened is we had a function, and we had a point on the graph of the function, and we wanted to find the slope of the tangent line to that point. And so we have a formula for dy dx that is a function in terms of theta. So we used the theta 5 pi over 6 and the derivative and the function and sine and cosine and plugged in the formula, and we got the slope of the tangent. So this is the first couple of pages of the section are devoted to this formula and the idea of using it, and they give you some stuff like where they'll say figure out where you might have a horizontal tangent line. Well, again, a horizontal tangent line is when the slope is 0, so I would set the numerator to 0 and see when that happens. Which angle values of theta will give me the place for the numerator. Or you might have a vertical tangent line if the denominator comes out to be 0, because that then gives you an undefined slope. Just things we used to do with tangent lines in general. But it all boils down to this formula and applying it to a function that's given in polar. So I'm going to stop this video here, and then we'll move on to the next video about integration and area under a polar curve after this.